All right, so today we're getting into a new type of related rates problem. Today we're getting into what we call a shadow problem, because as a person's running away, their shadow is increasing, and so that's this situation, which you hopefully have already written down into your work so that you then can just be focusing on the mathematics and the pictures that we do from here. All right, so anytime we've been doing a new problem like one of these, I've always started by just putting in, okay, what's the picture of this look like? So the first thing you might do is actually then draw a picture. Well, that might give you something that looks like this. If you're artistically inclined, as I'm afraid I'm not as much, but we got Homer running away from the street lamp and it creates a shadow. Now, one thing that I really want to bring home here, because sometimes we don't think of this aspect when we're just drawing the pictures, is remember the shadow starts at the person and then goes out from there. So only this much of it is the shadow, and it's created by where the person's feet are all the way up to where the light is crossing across the top of their head to end the shadow. And so notice it ends up creating kind of a triangle situation. The problem with this drawing, though, is that there's a little bit of extra flair to it. There's a little bit of extra going on in this drawing that we just don't need. Like Homer here, it's kind of hard to tell that that shadow should be going straight down and stuff like that. So we're going to make this drawing a little less interesting but a little more useful here. Basically, Homer's now just a line. Talk about being relegated. Well, he's 2D anyway. Maybe he just turned sideways. So we got the line here, but that represents where our person is. And so then I can actually start figuring out, okay, now I got triangles. Okay, so now I can actually think mathematically about it a little bit more easily. All right, now as I notice these two triangles, and yes, I do see it as two triangles. I got the little one here, but I also have this big outer triangle which includes part of that little triangle. How are those two triangles related? What do we call those two, geometrically speaking? Those two triangles, since they have the same angles, are similar.
Supplementary.
They're similar triangles. And since they are similar triangles, we also know that all their side lengths are proportional, which then is going to allow me to start getting into an equation using that idea. All right, now let's actually start dealing with what we have here. First of all, I want to label my unknowns that I'm supposed to be working with. So we got the length of the shadow here. I'm going to call the shadow S. Now, if I know the shadow is S, I also know all these other pieces here. So, like, I know Homer is 6 feet tall. I know the lamp is 18 feet tall. And he's running away at a rate of 8 feet per second. And I want to know how the length of his shadow is changing when he's 100 feet from the light. So this is 100 feet here. Now, if I start building this through, I can use the proportionality of similar triangles here, and I could write something like the height of the big triangle is 18, the height of the little triangle is 6, so I'm doing height over width, as it's so going to be. And so the width, well, that's where things get tricky with this. Well, the width of the little triangle, I already identified that as being S. That's my unknown. But then what would that make the width of the big triangle? This is where things get a little tricky, because it's going to, we would at first say 100 plus S. But if I do that, notice what's looking for again up here, what we're trying to find. How fast will the length of a shadow be changing when he is 100 feet from the light? I need to be looking then at also considering how fast he's moving away from the light. If I'm going to include this number, that's a derivative of this length. And so that's what sometimes can be a little bit tricky. I am going to give that particular length a variable name, and I'm going to use the variable for it. So I'm going to call this D for distance, just because I don't have a better name for it. You can call it X for all I care, but I'm going to call that D for distance. and then turn this into d plus s. And we're going to see why that is in a moment here. All right, so first line of my work. I wrote it as 18 over d plus s equals 6 over s. Now, I know I'm going to have to find the derivative of this with respect to time. If I do it right now, that's way harder than it has to be, though. Let's make this equation a lot simpler before we actually start calculating on it. You see how we do that? Cross multiply. Yeah, so let's go ahead and cross multiply right off the top here. So I do the 18 times s, which is just 18s, and the 6 times the d plus s. Make sure to distribute to both. And so you notice that once we get to this point, I can make it even simpler yet again. I'm just trying to make this equation as easy to work with and easy to find the derivative of as I can. And you notice that since I have an s just hanging out on both sides, I can combine those two. So I'm going to move that 6s to the left side. So technically, just to be super clear here, I am going to subtract 6s from both sides of my equation. That leaves me with a relatively simple equation then. 12s equals 6d. Now I can go ahead and find the derivative, which, because it was a fairly simple equation, is hopefully a fairly simple process. And so if I find the derivative of this equation, the derivative of 12s is basically 12, and then times the derivative of s with respect to t. So 12 ds over dt equals 6 dd over dt. Now remember what we're solving for here. We're trying to figure out how is the length of his shadow changing over time. So that means I'm looking for that ds over dt. So this stays 12 ds over dt. And that equals 6. What is dd over dt? That is how that d value is changing over time. So notice that is the 8, yes. And so then it's going to be 6 times 8. This is why I had to leave d as a variable in there, because if I know what the rate at which d is changing is, I have to leave d as a variable so that when I do the derivative, I can actually plug in that rate. So I didn't want to use the 100 right off the top. All right, so now go ahead and solve this for ds over dt. And so 6 times 8 gives me 48. 48 divided by 12 gives me 4. So it gives me an answer of 4 here. I do need units, though, because, of course, this is talking about a real-world type of situation. So S is measured in, well, that's the shadow length. So that's just measured in feet. T, I go up and I check to see what it is. By the way, notice I say I'm actually checking what it is because most of them have been seconds, including this one. Yes, it's also going to be seconds. But they aren't all seconds. So don't assume it's seconds. Actually go back and check to make sure that that's what it is. And so our final answer here is it is changing by 4 feet per second. And that's our final answer. Now, for those of you who just like an extra little bump in your thinking on this and would like something to kind of ponder over time, you notice that in all of this work we did over here, the 100 never came into it. So the rate at which the shadow was changing would be the same regardless of how far away from the lamp you were. Something to ponder about why that might be.